So uh, first of all, we have to count the total number of ligands, and then we have to tell the coordination number. And after that, we have to find out the oxidation number of a particular element in a complex compound. It's the same as we did in the previous units when we were discussing redox. So we used to find, let's suppose if we have an oxidizing agent that is going to be KMnO4. So we used to find the oxidation number of manganese in KMnO4, like let's say KMnO4. Since we know K is +1, it's in group 1, oxygen is always -2. If I'm going to put the value in K and oxygen, so I would be getting the oxidation number for manganese. So K plus Mn plus 4 oxygen is equal to 0. Okay. Since K is +1, Mn I have to find out. Since K is +1, K is +1 and Mn we have to find out, and 4 oxygen, each oxygen is -2 is equal to 0. So Mn would be equal to +7. Mn would be equal to +7. In this way, we used to find out the charge. We would be doing the same thing in a complex compound. We would be doing the same thing in a complex compound. Let's say this is the complex, and we have to find out the charge of iron in FeCN6. Okay, so since cyanide is the negative ligand in which the charge is -1, and the overall charge on a complex is -3. So we can see x plus 6 into -1, because cyanide is -1. X is the charge of iron. This is unknown, so I have taken it x is equal to -3. Why? Because the overall charge is -3. So then we can simplify this. So x would be equal to +3. It's very simple. It's nothing new. There is nothing new in the how to find the oxidation number in the complexes. But before finding out the oxidation numbers, we must know the charge of a ligand. Otherwise, it would be very difficult for us to find out the charge of a metal. Remember, since this is an oxalate ion, and we know that oxalate ion is a bidentate ligand. Oxalate ion is a bidentate ligand. So the charge of oxalate is -2. So the charge of oxalate is -2. So I have put the value of C2O4, that is -2. So I got the charge of iron, that is +3. Simple. Okay. Or let's suppose if I'm going to give you the value for this complex, formula for this complex CuH2O6 +2. And you have to find out the charge for copper. And you have to find out the charge for copper. So we know that water is a neutral ligand. We know that water is a neutral ligand. So copper is X. 6 water molecules I have. Water is 0 is equal to +2. So X is equal to +2. So the summary is that if you will be going to find out the charge for any particular metal, so you must know the oxidation number for the other substances. Okay. And then um, basically, as I told you that when copper reacts with a ligand, so they form dative covalent bond. You know, they form dative covalent bond. Then we have to discuss like the geometry of complexes. Then we have to discuss the geometry of the complexes. Geometry of complexes, we would be discussing that there are 4 types of geometries. Okay. Um, we have a linear complex as well. Then we have octahedral complexes as well. Then we have square planar complexes as well. And then we have a tetrahedral complexes as well. how can we find out the geometry of the complexes? So, we have to first write down the electronic configuration of a particular complex compound. In a complex compound, particularly the configuration for the metal ion. And afterwards, we have to see like how many electron pairs means including lone pair and bond pair we have. You know, lone pair and bond pair we have. So on the basis of that, we would be talking about the geometry of the complex compounds. Let's say this is the complex CuH2O CuH2O6, right? So since you have six water ligands, since you have six water ligands in it, okay, you can see. So copper is 29. The common configuration for copper is 3d10 and 4s1, and copper plus 2 is 3d9 and 4s0. 3d9 and 4s0. So what I did, uh, 3d9 means it has 9 electrons in a d orbital. It has 9 electrons in a d orbital, right? So I can say in which you have 5 orbitals. One, 2, 3, 4, 5, 6, 7, 8, 9. After 3D, you have 4s. After 4s, you have 4p, right? After 4p, you have d subshell like that, right? So since water is a ligand, water can donate one lone pair of electron. So water would be donating its one pair, whole pair of electron to this, that is 4s, to this, to this, to this, to this, to this, 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. You know why? Because they are empty orbitals. Because why? They are empty orbitals. So water can donate its lone pair. It's very simple. Okay. There is an empty space, so water will be donating its pair of electron to that particular you can say metal cation, right? So that's why we would say that since we have a six water ligands, water molecules, so the geometry of the complex is going to be uh, octahedral complex. It's going to be what? Octahedral complex. Okay. And afterwards we may have ammonia as well. You know, we have different sort of ligands. We have water as well. We have like cyanide as well. We have ammonia as well. So basically, we have to discuss the geometry that is going to be octahedral only according to the specification. They are saying that understand why complexes with six-fold coordination have an octahedral shape, such as those formed by metal ions with water, OH minus, and ammonia as ligands. Simple. And also with other ligands, we have to discuss the geometry that is going to be tetrahedral and then square planar. So I'm starting from octahedral complexes, that is CuH2O6. So I told you that if there are six ligands, if there are six ligands, so with the six ligands we have to draw the shapes of the complex just like that. This is called octahedral geometry. This is called what? Octahedral geometry, right? So this is the metal cation and these are the six total ligands and that's it. So this is an octahedral shape in which the bond angle is 90 degrees. Okay, number one thing. Another thing is that uh, what if I have this complex? What if I have this complex? And keeping in mind that If I would be giving you the complex such as Cu ammonia 6, like that. Again, the charge is 2 plus. So what you have to do, you have to replace water by ammonia, 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 and that's it. That's gonna be the octahedral geometry. Okay, not more than this. Only you have to know about that. If we have a six ligands, so we can arrange that ligands in an octahedral manner. Whether the ligand is water and whether the ligand is ammonia and whether the ligand is Cn minus means cyanide ion. Whether the ligand is what? The thing is that you have to arrange them in an octahedral manner where the bond angle is 90 degrees. Simple, okay? And then let's say if this is copper chloride, CuCl4 2 minus. You can see we have four ligands. You can see we have four ligands. So they can be arranged in such a way that the chloride ions would be at an angle of 109.5 degrees. Why 109.5 degrees? Because chlorine is electronegative element. And if you will be drawing this complex at 90 degrees or less than 90 degrees, might maybe 50 degree, maybe 40 degree, I mean to say like that, you know what would happen then? They would be repelling each other. They would be repelling each other. You know why? Chlorine is in group 7, so they have lone pair of electron. So they have lone pair of electron. So due to the presence of lone pair of electron, they will be repelling each other and they will be making that complex unstable. This is the reason to avoid instability, to avoid the repulsion, to become more stable. So the ligand should be arranged in such a way that there should be less repulsion and more attraction so that the complex becomes more stable. This is the criteria. And what if I have more than four ligands? I mean to say six ligands, like in an octahedral shape. So, you know, the complex compounds rearrange themselves automatically in such a way that there would be less repulsion and maximum attraction. So they will be setting themselves automatically. We are not supposed to do anything else. Just what we are doing, we are discussing how they are arranged in these manners. Some are octahedral, some are tetrahedral, some are square planar. So we are discussing this basically. Let me show you how the complexes are arranged. Let me show you. Wait, I'm sharing my screen. Um, okay, okay, yes. So you can see this. Okay. So this is like, let's suppose I'm selecting SF6. I'm selecting SF6, right? So you can see this is an octahedral shape, right? And you can see the bond angle as well. The bond angle is going to be 90 degrees. Okay. So, you know, let's say I want to distract the molecule in this manner, like that, and then this one, then this one, then this one, like that. So the complex would be rearranging itself in such a way that again the bond angle would be the same. See this? I am decreasing the bond angle, but it is rearranging itself to the 90 degree again. See this? Now it become more stable. That's why I was saying It's not a part of like it's not my job, it's not your job to decide the bond angle, you know, but we must know which complex compound has what bond angle. So the concept says if the geometry is octahedral, so the bond angle is going to be 90 degrees. Let's say, if I have a tetrahedral shape, that's it. That's a tetrahedral shape. You can see. So I'm distracting the molecule. I want to decrease or increase the bond angle, but when I would leave, so it will rearrange itself in such a way that the bond angle becomes 109.5 degrees. If you are thinking that, sir, how many molecules so that I can memorize? So you have only few geometries. As I told you, octahedral, tetrahedral, square planar, and linear. So I told you for the octahedral, where the total number of ligands are 6, right? If you have 6 electron pairs, if you have 6 electron pairs, so the geometry of the complex would be octahedral, irrespective of the ligand, what the ligand is. But I would be counting the total number of dative bonds. What I told you, if the dative bonds are 6. Of course, if we have 6 ligands, monodentate ligands, so the bond angle, like the geometry, would be octahedral. So in our specification, they have mentioned the 3 main ligands that you must know. Number 1 is ammonia. Number 2 is water. Number 3 is Cn minus. Okay, Cn minus. So, uh, and also, what if we have a bidentate ligand? You know, what if we have a bidentate ligand? That then what we would be doing? Okay, let me tell you that thing as well. But firstly, you can see this is the tetrahedral shape that we must know about that. The bond angle is 109.5 degrees, and this is the 3D shape. This is normal line, wedge and hash line, like that. Below the plane and above the plane. All chlorides are at an angle of 109.5 degrees. Okay. So if you are thinking that these two chlorine are near to each other, no, you are wrong, because this is below the plane and this is out of the plane. They are at an angle of 109.5 degrees because this is the 3D shape. This is the 3D shape. When you will see that shape as I've shown, so you saw over there that all the chlorides are at an angle of 109.5 degrees. Until or unless we can't imagine this situation after looking at the molecule in a 2D paper, so, but we must know, as I have shown, whenever I would be telling you about the tetrahedral shape, so we have to think that the bond angle is going to be 109.5 degrees. Not only for one, all the ligands are at an angle of 109.5 degrees. And then same goes with cobalt chloride. Rather than Cu, I have Co. Rather than Cu, rather than Cu, I have Co, that is cobalt. So nothing is changed. Charge is also same. Ligand is also same, but only the metal is changed. So this is gonna be the tetrahedral complex compound. Okay. Then we have this one, PtCl4 2 minus. Then we have PtCl4 2 minus. For the platinum complex, you know what we say about this complex, since we have 4 ligands, again the ligand is platinum. Again, the ligand is platinum. In the previous complex, the ligand was also the same, that was chlorine, but the metal was different, that was copper. But right now, the metal is platinum, not copper. So, you know, this is another theory. to determine the geometry, because more interestingly, the geometry of this complex is not tetrahedral. If you are thinking that the geometry is again the tetrahedral, so no, the geometry is square planar. Why the geometry is a square planar? Uh, we we are not supposed to know about that. We must know we must know an example that let's say which is square planar and which is tetrahedral. So especially for the platinum, it's going to be like the square planar shape. And one thing more, we have to discuss the isomerism as well. At that time, I would be telling you about like the concept of cis and trans. Okay, what is cis and what is trans? I would be telling about that. But right now, you must know if there are four ligands. If there are four ligands, so the geometry is supposed to be the tetrahedral and it is supposed to be square planar as well. And you have to memorize all the examples, including copper chloride, including cobalt chloride, including platinum chloride. So cobalt and copper chlorides are tetrahedral and the platinum is going to be square planar. Okay. And the shape of the square planar is just like that. This is the 3D shape of square planar where the bond angle is where the bond angle is 90 degrees, where the bond angle is 90 degrees. Okay, so you must know about that. You must know about that. Okay, so we are more specific towards like the geometries. We are not supposed to know each and every complex. No, you have to know with the ligand that is going to be chloride. Okay, and let's suppose um, if we have a bidentate ligand, just like that. This is a bidentate ligand, isn't it? If this is a bidentate ligand, so one EN can make two dative bonds with this copper. One dative bond, one ligand can form two dative bonds because this is a bidentate ligand. This is the first ligand, this is the second ligand. So we have two bidentate ligands. If we have two, if we have two bidentate ligands, so of course they will be forming four dative bonds in total. Again, again, you can see the coordination number is the same, isn't it? Again, you can see the coordination number is the same. So that's why I'm saying it's your square planar complex. Let me show you some more examples that we must know regarding the geometry of the complexes. Okay. So as I told you about the square planar as well, and square planar is the example of a square planar is platinum chloride. Then later on we would be discussing the concept of cis and then the trans. Okay. Or see this one. What if I have chromium? Just look at this carefully. What if I have chromium, right? And let's say one, then two, then three, then four, then five, and then six. This is going to be the chromium. And see this one. Okay. I can say like this, and then like that, or like that. See this. Let me show you how many ligands we have. Since, by the way, the overall charge is -3. By the way, the overall charge is -3. So I want to show you here that we have three bidentate ligands. We have three bidentate ligands. This is the first ligand that we have. This is the second ligand that we have, and this is the third ligand that we have. But they are forming six total dative bonds with the metal cation. So I would say that the geometry is octahedral. I would say that the geometry is octahedral. You can see, you can see one, two, three, four, five, six. Total six dative bonds that are say they are going to form. So, but we must know which ligand is what, which is monodentate, what is bidentate. And what if I told you in the last class, in yesterday class, about EDTA? Since EDTA is a hexadentate ligand, if you will see the complex of hexadentate, so one EDTA is more than enough for the metal to give you the octahedral geometry, right? Because EDTA can donate six dative bonds towards the metal cation or okay. So these are an examples of octahedral shapes with different ligands. We might have monodentate ligand, we might have bidentate ligand, and we might have polydentate as well. Okay. And also, uh, let's say if I have this complex AgNH32, Ag AgNH32, the overall charge is +1. The overall charge is +1. Okay. I can draw AgNH3 and AgNH3. You can see there are two bond pairs. You can see there are only two ligands. How can I arrange these two ligands with the metal cation? So there is only one possibility to make a linear complex. We can't draw tetrahedral shape. We can't draw square planar. We can't draw octahedral. We can only draw the linear shape. So the summary is that. So the summary is that. Let me write. Number one. Number one thing is that um, if total six ligands you have, uh, to make it more simple, if we have total six dative bonds between the metal and a ligand. So you know the geometry is going to be octahedral. And if we have total, if we have total four dative bonds, you know, the geometry would be of two types. Might be tetrahedral and might be square planar. To be more specific, you have to memorize. Okay. Otherwise, this is very complicated chemistry behind it. Like, how can we decide if the anonymous compound is given? Of course, in an Excel, they are more specific towards the geometries. That is, I think, so more simple. You know, this is more simple. So there are two tetrahedral complexes that I told you. So copper chloride and then cobalt chloride with the four dative bonds between the metal and a ligand. Okay, and I told you one example of square planar complex, that is PTCl4 2 minus, isn't it? So this is square planar, and the copper ones were like the copper and cobalt chloride ones were tetrahedral geometries. Okay. And what if we have total, total two dative bonds? So, it's going to be linear shape, linear shape, where the bond angle is 180 degrees, and in a square planar, the bond angle is 90 degrees. In tetrahedral, the bond angle is 109.5 degrees. And in octahedral, again, the bond angle is 90 degrees. Okay, simple. So this is an overall summary of the geometry of complexes. You're not supposed to know about many complexes, remember, with many examples. Okay, it's very simple. And then let's talk about the isomerism. It's a very vast topic. Again, I would say to be more specific, according to the specification, basically, hopefully you previously knew about the cis and trans concept. In organic chemistry, we used to discuss cis isomer and also the trans isomer, if you remember, cis isomer and a trans isomer. Cis means we used to say when the two groups are attached on the same side, and trans means that when the two groups are attached on the opposite side. So the same goes here. The same goes here. Remember, you know how we will be discussing about that. Let me show you about the platinum complex. Let me show about the platinum complex. So if you will see the platinum one, that is PtCl4 2 minus, PtCl4 2 minus, and if we have two chlorine and two ammonia, they are more specific, PtCl2 and NH3 two chlorides and two ammonia. This is more specific complex, two chlorides and two ammonia. Let me write it down. Wait. PT, okay, and this is Cl, NH3. Okay, you can see the two chlorine are on the same side. You can see the two chlorine are on the same side. I mean to say at an angle of 90 degrees. So this is going to be the cis isomer. And if and if the different groups are at an angle of the same groups are at an angle of 180 degrees. I mean to say this one. So this is going to be your trans isomer. The concept is same, by the way. You're not supposed to learn any new concept about the cis and trans isomer. So this is very good thing about that. Okay. So let me summarize it. We have to discuss the two types of isomerism as you did in the organic chemistry as well. So we would be discussing the two types of isomerism. Number one is geometrical isomerism, that is also known as cis-trans isomerism, and another one is optical isomerism, right? So for the geometrical isomerism, let me tell you one thing that is very important in this complex. So let's do this complex, especially more specifically this complex, right? PTNH32 and then Cl2. So two same ligands and two same ligands. Like there are two different types of ligands in this complex. If they are on the same side, so I would say cis. And if they are on the opposite side, so I would say trans. Okay. You know, for this complex, we have to discuss some other things as well. It's an anti-cancer drug. You know, it's an anti-cancer drug. What it would do, what it does. This is more important to know about this, especially cisplatin complex. I'm only interested to discuss about the cisplatin, not the trans one. Remember, remember. So what I have written over there, it's a cisplatin. It's an anti-cancer drug. It reacts with DNA molecule. It reacts with DNA molecule. And since it contains some sort of different groups, so in this reaction, it would be behaving as an anti-cancer drug. So this is more specific. Only the cisplatin. You must know about the cisplatin only, not other than this. Of course, this is more easy because the syllabus is more specific. This is not random. This is not random. Okay. Okay. Then after discussing this cis trans isomer, then we have stereoisomer. Then we have what? Stereoisomer. Let me tell you about the stereoisomerism. Stereoisomer means when you have mirror images. When you have mirror images. Mirror images means what? As we discussed in the previous classes, um, let's suppose I have this complex, right? Listen very carefully about that. If I have this complex, so let's suppose the mirror image of this complex is this. The mirror image of one is this. They are mirror images of each other. They are mirror images of each other. Why? Left becomes right. Left becomes right and right becomes left. Simple. They are mirror images of each other. When I will be taking this mirror image and will be overlapping this mirror image onto this complex, is this overlapped? No, this is not overlapped. You can see not 100% overlapping. They are not superimposable. We used to use the word superimposable or non-superimposable. So the two isomers are non-superimposable. That's why they are the mirror images. Otherwise, I'm not supposed to say that this is the mirror image of this complex. So we have to do this. We have to superimpose it. If they are completely superimposable, so I can't say that they are an isomer of each other. So this is the main condition of the stereoisomerism. They must be superimposable. They must be non-superimposable. Let me show you an example in which they are non-superimposable. Uh, or. Okay, let's say, let's say you can see this one. You can see this one. If I will be superimposing this on this, Is this superimposable? No. You can see. You can see this is OH, this is Br. This is non-superimposable. So yes, if this is non-superimposable, I would say that this is an optical isomerism. Okay? You will get an idea. You will get an, this is also optical isomer because non-superimposable. You can see. You can see. Non-superimposable. When you will see the superimposable example, so 100% they will be overlapping with each other. That's the concept. That's the concept. Okay. So let's suppose if I have PTCl42 minus, I'm going to draw the shapes like that. Okay. And I'm saying it to you that they are the mirror images of each other like that. If I'm going to superimpose it on that complex, oh, they are 100% superimposed. The same ligands are overlapping. The same metal is overlapping. If everything is same and then they are overlapping to each other, so I would say that they are quite perfect superimposable. So I'm not supposed to say that they are optical isomers of each other. No, for the optical isomer, what we are supposed to do, we must have mirror images. And what are mirror images? What are mirror images? How can I define it? The mirror images means when they are non-superimposable on each other. So you have discussed in unit 4. That's why I'm not going to tell you from the scratch what the cis trans isomer is, what the optical isomer is. We did in a detail in the previous unit. So we are only applying that concept on the complex compounds. We are applying that concept on the complex compounds, and that's it. Okay. So then afterwards, we have some examples. Let's say monodentate, bidentate, hexadentate. More specific to, I told you, bidentate one was oxalate ion, and then polydentate were EDTA. So, examiner would be giving you the geometry of the complex and would be asking about that. Cis trans is possible or not? Optical is possible or not? So, of course, we discussed specific complexes, of course. We discussed specific complexes. So he would be asking specific complexes, not all of the complexes. Okay, this is understood. We would be doing the past paper. You will be getting an idea, by the way. Okay.